Hi, everybody, and welcome to MTED 110. This is the first lecture of the semester, so I hope you enjoy it. Just some introductory ideas, introductory concepts, and we'll go over some basics about what the course is going to be like. We'll also talk about how to view these lectures themselves. So let's go ahead and get started. All right, so these slides you can find on Beachboard. You can follow along if you'd like. You can observe them here on the lecture itself. It's totally up to you. There's a lot of flexibility in this course, as you'll see, and I'll kind of mention it in a minute. But let's start with this. So from an etymological standpoint, which kind of means the study of how words are constructed, think about it like that. The word mathematics comes from the Greek verb monthano, which means to learn, to which two suffixes are added, ma, meaning the thing being learned, and tix, meaning the craft of. Hence, literally, mathematics is the craft of learning things. So as math educators, as math teachers, we are quite literally teaching people how to learn things. It's a very important and powerful skill to impart upon your students. And so I hope you view it with some reverence and some degree of seriousness. Um, Another thing, here's a definition of the word pedagogy or pedagogy. Some people pronounce it differently. Pedagogy is the method and practice of teaching, especially as an academic subject or a theoretical concept. Oftentimes in this class, we will be discussing pedagogy, which means how you teach something, what's the most effective way of teaching something, and so on. This is also a content course, so the primary goal of this course is to deliver a bunch of content about the mathematics that children need to learn and how you would teach children to do that type of mathematics. So it's going to be a fun journey. I'm glad you're here to go along. Let's see, where were we? Okay, so first, welcome. The syllabus is on Beachboard. You should make sure to read that. We went over it in the orientation meeting, but a lot of times if you have questions, you can find the answer in the syllabus, so make sure to check there. For WebAssign, I gave a complete tour of how to use WebAssign and how to access WebAssign at the orientation meeting, so you should check out that recording if you're having trouble getting WebAssign to work or you're wondering about the format there. This is my main bit of advice for the entire course here, and it's just you need to keep pace. Keep pace. And I'll say that a lot as the course goes on. This course is designed not to overwhelm you with content and beat you down with new things to learn. It's designed to introduce you to new things at a very steady rate. But if you don't keep pace, what ends up happening is you end up trying to pile a whole bunch of stuff at the end and you don't do anything at the beginning, and it really doesn't work out well, trust me. So the main thing you need to do is keep pace. Keep pace with watching the lectures and doing the activities, and keep pace with the WebAssign homework. You should be doing a little bit of the WebAssign homework every day. Don't try to save it all until right before the module assessment, trust me, all right? Also, you should avoid memorization. Mathematics in general is not about memorization, despite what some of your teachers might have told you in the past. We'll actually talk about that at great length in this course, but I'm not quizzing you or testing you or assessing you on anything about memorization, really. There are some terms that you'll need to memorize, some terminology, some vocabulary, but that's pretty much about it. I'm not expecting you to memorize formulas. The things that will show up on the assessments, well, for one, I'll tell you about them, but it has a lot more to do with explaining your thinking, explaining your reasoning, and modeling something appropriately, as you'll see as we go along. Oh yeah, there you go. Demonstrate your understanding by explaining your thinking. That's more of what this course is about. And then this is a big one. You should always be asking why. You should always ask why in any situation for any reason. You should never stop asking why. And more importantly, you should be demanding answers. You should be demanding answers from people. Don't believe anything that anyone says. If somebody tells you something is true, ask them why and ask them to explain it. Because for one, that's what your students are going to do, your math students when you're your own teacher, right? And we deserve a right to an answer. So make sure to ask why. And I encourage you to ask me why about anything you want, and I'll do my best to answer. And if I don't know the answer, I'll tell you I don't know the answer. So some of the course goals, these are in the syllabus. I just want to I kind of wanted to review them really quickly. I want you to gain comfort in exploring mathematical topics, asking why and how. All teachers, in other words, you in the future, you're going to come across new and challenging material during your career, and you should be able to gain an understanding outside of an academic setting. What that means is that you shouldn't, as you go along, you shouldn't need a course to learn new mathematics as you get a little bit older and more advanced in your career. And the way that you achieve that level is by gaining comfort with exploring mathematical topics, asking why, asking how. So we'll do that a lot in this course. Yeah, just keep asking why. Demand the answers. Demand the answers. I really, really hope that you will leave this course seeing mathematics as a system which makes sense and not just a set of rules to memorize. This is one of the things that crushes my heart is that students leave the K-12 education system in America feeling that mathematics is just some random set of rules to memorize and it doesn't really make sense. You just have to remember which formula to pull out at the right time and which trick to pull out at the right time. And that was my experience going through K-12 education too. And then when I got out of K-12 and got into college and went further and further, I realized that that's really not at all what mathematics is. Mathematics is a language, and we use it to describe ideas and communicate with others about those ideas in a very, very precise way. That's what it is. So no memorization. It's not just a set of rules to memorize. Just keep that in mind. I also hope that you'll develop an appreciation for the mathematics classroom as a venue for creativity, problem solving, exploration, inquiry, collaboration, and discourse. We'll talk more about pedagogy in this regard because a lot of people are used to an old hat style of education, which is really just a bunch of lectures, right? A professor lectures at you for an hour and 20 minutes, and then you go home and do homework, and then you come in and you take a test. It turns out that that method of education is not very effective for most learners. I try to keep my lectures short, but I can be long-winded sometimes. And what you'll notice in this course actually is that some of the lectures are long, but other lectures are extraordinarily short, like just a few minutes, or maybe like 10 or 15 minutes. So keep that in mind, and I'll try to give you all a heads up if I can during the meetings to say like, oh, the next lecture is a long one, so make sure you set aside like an hour tonight to watch it. But yeah, the mathematics classroom is a place for discovery, not just a teacher lecturing at you. And that's one of the reasons I structured this course this way. I'm going to sit here and lecture at you in these videos, but we'll talk about how you can kind of get around that in a minute. But then the real learning occurs in our collaboration meetings and in the collaboration meetings with your group members. That's where the real learning occurs. So that's really what our classroom is. And our classroom is not just a single classroom right now, right? Oh, yeah, I also hope that you'll leave this course embracing problem solving in mathematics as a creative activity in which there are many valid approaches. There's rarely one valid way to solve a problem. And what you're going to see in this class is that there are many, many ways to solve problems. And we actually encourage our students to come up with their own ways and explore other ways and try to figure all those things out. We're no longer in the the era where if a student doesn't do it this one way, then they're wrong. That's the old pedagogy from back when I was a kid. That's not really what we're about anymore, at least not in this country, and especially not in this state, California. Um, I'm hoping you'll also be able to improve your ability to communicate with and about mathematics. I think that one's pretty straightforward. And this is a big one too, because this will be part of your job as a math educator. Realize that if a student knows how to perform an algorithm, that doesn't necessarily mean that they know, or I shouldn't say, I mean, it doesn't mean that they understand the underlying mathematics. It does not mean that they understand the relevant mathematics. So one of the things we realized in recent history, this had to do mainly because of had to do with mainly the political decision called the No Child Left Behind Act. And after that act went into place, and after we had a whole generation of students, we ended up with students in this country that were really, really good at regurgitating algorithms and throwing out these random tricks, but they really didn't understand what they were doing when they used those algorithms. And the problem with that type of mentality is that we have these things that are able to do algorithms and compute problems a lot faster than anyone ever will be able to. And it's phones, it's computers. These things can do all the calculation. I mean, that's really what it is. What we need is we need people to understand what's going on when those calculations are occurring. And we'll focus on that a lot in this course. I think it's really, really fun, honestly. I hope you do too. Okay, so let's talk about how to watch these lectures, the one that you're watching right now. So first off, what I recommend is that you watch them as a group. I mean, heck, I can play this lecture right now in a Zoom meeting and we would all be watching this video as a group. That's one of the reasons I don't want to spend all this time just lecturing at you live because I feel like our time could be better spent by us talking to one another, right? But there is content that I need to deliver, and I'm going to deliver that through these lectures. So to make the most out of these lectures, I highly recommend you watch them as a group. Open up a Zoom meeting, call in your group members, start the lecture video, and you all can sit there and talk while you watch the video, and you can make fun of me and all sorts of things, right? Pause whenever you want. These are videos that are pre-recorded. You can pause them. You can pause them as often as you want, as little as you want. So don't feel like you have to, that you have to like keep pace with the lecture. You just have to pause it when you get stuck. And you can use the captions in the transcript. So each one of these videos has captions, and I downloaded and uploaded a transcript. It's not the best format, I don't believe. I'm going to see if I can make it better, but you can use those to your advantage too. If you don't want to listen, you can always read instead. You can also watch these videos at 2 times the speed. I know a lot of students like to do that. I've done that in the past where you don't really need to hear me drone on at my normal voice. You might want to hear me drone on in this voice. So you can always watch it at 2 times the speed if you want. In general, just get as much out of it as you can. These lectures are for you. They're a resource for you to use to understand the content in this course and to help you get through this course in an edifying way. Now for questions, this is the important thing. If you're watching a lecture, hopefully with your group, and you have a question, just take note of the slide number. All the slides are numbered down there. And so if you have a question or if you want to ask me about it in the collaboration meeting, you could pause the lecture, think about it, talk to your group, and then you can be like, okay, let's ask them about this. Okay, this is what, lecture 0, slide 6. So then in the collaboration meeting, you can say, oh, hey, Mr. Richardson, can you go to lecture 0, slide 6? And then I'll be like, sure, no problem. And I'll pull that up and we can talk about it live then. That's how it goes. Now there's also these things that I call Dora moments. So some of you might be familiar with the show Dora the Explorer, or Daniel Tiger, if you've seen those, if you've worked with children. And what happens in those shows is Dora or Daniel Tiger is introducing a concept, and then they'll look at the camera and they'll ask the camera a question, and then they'll pause for about 10 seconds with these like funny blinks. And that's so that people, the kids in this case, have a chance to respond to the video. So we're going to do that here also, but obviously, you won't be talking to me personally. Hopefully you'll be talking to your group members as you watch the lecture. And what I'll do is I'll basically give you a warning that a Dora moment is about to occur. And what I'll do is I'll pop up this, this little symbol right here, the thinker. And I'll just pause for about 10 seconds. And then what I'd like you to do is to pause the lecture at that point and then think, just like the thinker is showing you there. And after you've thought about the question for a little while, the next thing that I want you to do is talk about it, say it out loud. Even if you're alone in your room, just say some words out loud about what you're thinking. And this is also why it's even better if you're in a group, because if you're in a group, then when you talk, you can talk to somebody else. You wouldn't just be talking to yourself, right? So that's what those 2 symbols mean. Those basically indicate a Dora moment where you should pause the video, think about what the question asks, work out your answer to the question, and then continue with the lecture. All right? So that's the idea. That's the idea there. Okay. Okay, so let's start with a little bit of perspective. Let's get to some content. Hopefully you went through and did that short activity that I sent out earlier before the course started. And it had to do with this research project done where expert mathematicians were stumped by simple subtractions. And the idea here was that a simple arithmetic problem was presented to a lot of professional mathematicians, and I think it was 24 or 25% of them thought that the questions were unanswerable, or at least one of them was unanswerable. And there's a reason for that. Let's recall what those questions were here. Let me see. Yeah, there we go. Okay, so the first one was this. It said, Sarah has 14 animals, cats and dogs. Midna has 2 cats fewer than Sarah and as many dogs. How many animals does Midna have? And hopefully you went through and did this activity and just kind of pondered which one of these questions was more difficult. Let's read the second one. When Lazy Smurf climbs onto a table, he attains 14 centimeters. Grumpy Smurf is 2 centimeters shorter than Lazy Smurf, and he climbs onto the same table. What height does Grumpy Smurf attain? Now, one of the things I noticed, and hopefully most of you noticed also, is that one of these questions was easier to answer. And it depends on who you are. It really depends on who you are, and that's the whole point. That's the point of this this perspective here is that it depends on who you are and how your brain works and what kind of thinker you are. For me, I found the second one to be much easier than the first one, but that's just me. And I found this one to be extremely hard for some reason. But it took me like several minutes before I realized that the question was actually much simpler than what I was making it out to be. And that's the whole point. That's the perspective. This one was also the one that stumped the mathematicians. And a lot of mathematicians said that this question right here, oops, let me use this, that this question right here was not answerable. But it is. It's really just a subtraction problem. Incidentally, the problem that's being modeled here is the subtraction problem 14 minus 2, which is 12. So the reason that one of these feels easier than the other for most students is that they're touching on different cognitive abilities. Let me explain for a minute here. The second question here, the second question here really relies on your ability to almost imagine a continuum. So when you see this, you might be imagining like a ruler or axes, right? Like axes, like a y-axis. And you can imagine a person and you're measuring their height, right? So this one is almost a continuous problem because the picture you're thinking of is like a continuous line that's a certain height. Now, this one is actually pulling from a different cognitive skill. This one is asking you to do something that's discrete. Discrete meaning individual point data, right? You've got exactly 14 animals, and animals are discrete things, right? You can't have like half of an animal or a third of an animal. So automatically, you're pulling on something different. You're talking about discrete objects as opposed to a continuum like you do down here. And this is the one that really threw people off. So if one of those was easier for you and one of them was harder, I encourage you to think about why and think about the structure of these two problems, because that's really what's going on. And what's interesting here is I'm absolutely 100% certain that all of you could compute 14 minus 2, which is 12, right? But some of you probably struggled a lot with one of these problems. And that's the whole idea. That's the perspective. It's not that you don't know how to do subtraction. It's that the way the problem was presented might not jibe with the way your mind is working at that time, right? So these are important things you have to keep in mind when you're working with your students in the future. Yeah, so being a teacher requires a robustness of knowledge, and a lot of people seem to be unaware of just how robust this knowledge needs to be for you to be an effective teacher. We have this nice little chart here, and this is a chart of the mathematical knowledge for teaching, or MKT. I can zoom in a little bit here. There we go. So there's two halves to this picture, right? And they're split right here. So on the left, we have subject matter knowledge. Subject matter knowledge is just knowing about the subject you're going to teach. Because if you're going to teach something, you better know a lot about it, right? And then on the other side, on the right-hand side, we have pedagogical content knowledge. And that's essentially knowing how to teach a concept, right? So even if you're really good over here on the left, if you know a lot about the subject that you're teaching, maybe you're an expert in the field and you're teaching that subject at a university or something, that doesn't mean that you have good pedagogical content knowledge. And this is actually why some of you have experienced this before. And if you haven't, you'll experience it at some point, I'm sure. Sometimes you'll find that teachers are really good at what they do, meaning like if you've got a math teacher and they're really good at math, or you've got a physicist who's really good at physics, but they have a lot of trouble explaining how to do what they know how to do so well. That's the difference between a good teacher and a poor teacher, essentially. So if you don't have this right side, then it's difficult to be an effective teacher. You need more than just subject matter knowledge. You also need content knowledge, pedagogical content knowledge. So let's take a look at some of these bits here. Let's just focus on the subject matter knowledge for now. First, you need to know common content knowledge. That's just knowledge about anything common to all of the content that you're talking about. Horizon content knowledge is knowledge of what's going to happen on the horizon. So imagine, like a question is, why do we teach students to do addition in this way? Or multiplication in this way? Or why do we teach them about fractions in this way, ways that we'll explore in this course? Well, the reason is because I'm looking out at the horizon and I know where they're gonna be in the future. And you are gonna need to know where they're gonna be in the future, because what you do now influences what's gonna happen in the future. And that's what you have to think about. That's what you have to think about. That's horizon content knowledge, and we'll talk more about that as we go on. And then there's also specialized content knowledge. And specialized content knowledge is knowledge of content that is specific to individual, what do I want to call them? I want to say concepts. For example, if you needed to teach how to complete the square, if you're doing high school level math, right, or middle school level math, if you needed to teach how to complete the square, that's a type of specialized content knowledge. It's not so straightforward as just adding some numbers together, right? You have to know about that specific process and be able to explain that specific process. And that's actually leading us over to this side, pedagogical content knowledge. Oops, sorry, pedagogical content knowledge. Um, okay, so pedagogical content knowledge is much more fuzzy, you could say, or nebulous. You need to have knowledge of content and students. You need to have knowledge of content and teaching. And you need to have knowledge of content and curriculum. So notice that all of these talk about knowledge of content as well, except they add in these other people, essentially, students and teachers, and then the curriculum. So what this means is that you need to know not only about that content, but you need to know about the students that you're teaching it to. Who are they? What grade level are they? What age are they? Where do they come from? Where's their background? All of those things. Same thing with teaching. You can't teach a first grader the same way that you would teach an eighth grader, for example. So you need to know how to teach certain concepts at certain levels based on what you're teaching and when. And then lastly, knowledge of content and curriculum. So there's a curriculum set up at every level of education, and you have to know about how what you're teaching fits in with that curriculum, and if you're staying aligned to the curriculum set out by the department, the school, the district. All of these things are things that you have to consider, and they fall under the umbrella of pedagogical content knowledge. See, that's the thing is a lot of people feel that teaching is just this, know a lot about a subject and then go talk about it. But that's not the case. It's the whole shebang, right? The whole 9 yards. You need the whole MKT. Okay. Um, so teachers need to know a lot. So they need to know general pedagogical knowledge with special reference to those broad principles and strategies of classroom management and organization. That's a difficult job. And when I interview students that want to enter the single subject credential program at Cal State Long Beach, one of the first things I ask them is, how much experience do you have with children, and do you enjoy managing large groups of children? Because when you're teaching at the K-12 level, classroom management is a huge part of your job. And this tends to hit some potential applicants kind of hard because they might really, really love math and they might be really, really good at tutoring math, right? Like, oh, I love tutoring. But then the question is, could you instead deal with 30 of those kids and manage them all and still teach them that math? That's the question. They need to know, teachers need to have knowledge of learners and their characteristics. What's the difference between an elementary schooler and a middle schooler? Because there's a huge difference. What's the difference between a middle schooler and a high schooler? There's a huge difference. And to gain some perspective, just think about how you were in elementary school, and then think about how you changed when you got into middle school or junior high, and then think about how you changed again when you were in high school. And now think about what it would be like if you had a high school teacher teaching you when you were in second grade or vice versa, right? It doesn't really work well. So you have to adapt to your students, and teachers need to know about their learners and their characteristics. Knowledge of educational contexts. This is another big thing. Teachers need to have knowledge of these educational contexts, ranging from workings of the group or classroom, the governance and financing of school districts, to the character of communities and cultures. So this is another thing that K-12 teachers have to be very familiar with. You need to know how the classroom is going to work together. You need to understand how the district is financing your ability to actually teach these courses, all of that stuff, all that stuff. The character of communities and cultures. Schools are not all in the same community, and the people are not the same in every community you go to. So if you've got a school situated in one community, you have to be familiar with that community because those are your students. That community is your set of students. So you have to have that type of knowledge to be a more effective teacher. Knowledge of educational ends, purposes, values, their philosophical and historical grounds. Why do we do it that way? Historically, how have we done it? What's worked in the past? Does it still work now? Sometimes you'll find that it doesn't work now anymore. Content knowledge, which we talked about. Curriculum knowledge with particular grasp of the materials and programs that serve as the tools of the trade for teachers. Once you've been teaching for a couple of years, you'll realize that there are some tools of the trade that everybody uses at that level or for that class, and you pick up on them as you go along. This is where, for those of you that go into the single subject credential program, this is where your master teacher is really, really helpful because they're the ones who know the tools of the trade and they're going to try to teach them to you. Pedagogical content knowledge, we talked about the special amalgam of content and pedagogy that's uniquely the province of teachers, their own special form of professional understanding. Uh, how children think, uh, learn, and grow. For example, when are children ready to learn multi-digit multiplication? What grade level? Kindergarten, first grade, second grade? That's a good question. You got to know that. You got to know that as a teacher. You also need to know about the content that you teach. So for example, what is 49 times 25? You should be able to compute that. So you do need to be able to compute that actual problem. And then this is the big part. Does this child's solution to 49 times 25 make sense? Does it make sense? That's the question. Because a lot of your students will do a computation and maybe they get the right answer, but the question is, did what they did make sense, or did they get lucky? So let's try this. Let's have our first Dora moment, okay? So what I want you to do in your group or on your own here is just take a few seconds or a few minutes to compute 49 times 25. Just go ahead and compute it. Okay, now if you've computed it, the next thing you want to do is I just want you to talk about it out loud. Say what you did to your group members or say it out loud to yourself. Just go through your actual calculation. And while you're doing that, I'm going to write up the solution right here. I'm just going to use the standard algorithm. Why not, right? Let's try it. 49 times 25. Standard algorithm says to do this, right? Okay, add those up. 1225. So I was able to compute that. There we go. Okay, now what's next? Okay, so take a look at these 3 student attempts to solve 49 times 25 or to compute 49 times 25. And what I want you to do is I just want you to look at each of these 3 attempts and ask yourself this question: what went wrong here? See if you can figure out on your own or with your group, better yet, what was going on in the students' heads. That's one of the fun things about being a teacher. You kind of wonder, like what we talk about in the faculty lounge. A lot of the times we're looking at our students' work and we're trying to figure out what they're thinking to see where their brain is at. Because we're like, oh man, how did they come up with this? Like, what, where did those come from? I can't see where those came from. Can you see where those came from? And then your colleague will look at it and they'll be like, oh, let me think about that for a minute. And that's a lot of what we talk about. So what I want you to do right now is the same thing. I want you to look at these three computations and see if you can figure out what went wrong here. All right, so go ahead and try that. Okay, and now that you've thought about it, hopefully, and uh, figured it out or thought about it yourself, now what I want you to do is I want you to just talk about it. Talk about it out loud with yourself, or talk about it out loud with your group as you're doing this right now. All right, now let's us talk about it right now. There are lots of different interpretations, and actually, what I'm going to ask is that some of you come to the collaboration meeting and tell me what you thought about it. Right? What did you think about it? Let's see what we got here. This one, let's start with B. A is an interesting one, and there are a lot of different interpretations of A, but let's look at B. Notice that they got 225 here, and then they got 100. One of the things that we teach students is how to split numbers up into meaningful chunks, and we're going to focus on that a lot in this course, actually, so be prepared for that. But what I notice here is this. If you do 25 times 9, that's 225. And then if you do 25 times 4, that's 100. So maybe that's exactly what this student was doing, 25 times 9, and then 25 times 4, and they wrote down 100. And then they added those two things up, and that's how they got 325. Now, that's not the right answer, right? We know that the answer is 1225, so what went wrong there? What went wrong there? I'll let you think about that. Um, this one over here, part C, is also interesting, right? They got 1250. Where did they get 1250 from? Any ideas? Hopefully you thought about it and talked about it, right? Well, think about it like this. If this were a 50 instead of a 49, 25 times 50 is 1250, right? You can compute it if you want. Maybe the student computed it in their head or they did something off to the side. That's totally fine. And then they did this 25 at the bottom, and that has to do with what they were adding to this 9, because we don't have 50. It's not 25 times 50, it's 25 times 49. So that's one too many 25s. And it looks like what they meant to do here was subtract. And if you subtract 25 from 1250, you'll get the right answer. But that's not what they did. They added. Maybe they added because they know that the algorithm is supposed to be addition. The algorithm says to add, so I always add, right? That's what the algorithm told me. Interesting. Either way, that method did not lead them to the correct answer, even though there was some clever computation going on. So that's why it's important to look at these details. Okay, now let's go back to number one, part A, student A here. Now, this one is interesting because you can see a lot of different possibilities, and I'm curious to hear what you think. But one of the things that jumped out to me when I first saw it based on my experience was this. 9 times 5 is 45, right? Well, that's what this student wrote. The student wrote 45. Yeah, yeah, you see that? It says 45 right there. Maybe this student is having language acquisition issues because they wrote 45 almost phonetically, you could say. But then they did something else down here. Notice they did 108. Where'd they get the 108 from? Well, maybe that's where this comes in. 2 times 9 is 18, or it's 10 and 8, right? 10 and 8. Well, that's 10 and 8 right there. 10 and 8. So maybe it's a language acquisition issue combined with knowing that they're supposed to put zeros somewhere. Notice there are no like placeholder zeros here. The standard multiplication algorithm tells us you're supposed to put placeholder 0 there, right? But why? Why? That's the whole question. You actually don't need it, as it turns out. So maybe that's what's going on here. But I'll be curious to hear what you all thought as well. So please come to the collaboration meeting and tell me what you explored or what you figured out. So now let's try this one. So in these three cases, the students got the correct answer. They got 1225. The question is, are these methods valid? Oops. Are these methods valid? In other words, would you tell your student to keep doing it this way? If they showed you this work and you read it and you were like, huh, would you then say, that's really good, keep doing it that way, keep doing it, try that out? So yeah, here's another Dora moment, right? So just go ahead and take a few minutes and see if you can figure out if these methods are valid or if the student got lucky. Okay, so now that you've thought about it to yourself, the next thing I want you to do is I want you to speak out loud about it. So talk to yourself or talk to your group members, either way. Okay, now let's talk about it. All right, let's see. What's this first person doing? 49 times 25. Oh, look, they did something similar to what person B did, student B. It's very similar to this, right? Oops, actually, I want to use this. It's very, very similar to that. You see, they did 225. Oops, they did the 225 right there, just like this person did over here. There's the 225. And then they did the 100, but they remembered the zero. They remembered the placeholder zero, right? So now if you look back at this, that's what went wrong here. This student forgot that placeholder zero that's supposed to go right there. And if they had remembered it, they would have gotten the right answer. So this perfectly emphasizes the difference between understanding how to multiply and understanding how to do the multiplication algorithm. What this bit of data tells me about this student is that they do know how to multiply, and they actually are pretty good at multiplication because they can see that you can split these numbers up into meaningful or easier to deal with chunks and work with them separately. But what this also tells me is that they're not comfortable with the standard multiplication algorithm. That's a huge distinction right there. This is a student who does know how to multiply. They do understand multiplication, but they're not that good with the standard multiplication algorithm. Maybe we can give them a different algorithm that's more easy for them to follow or makes more sense to them. Okay, let's see. Next, oh, part B, this is just the standard algorithm. Student B, sorry. That's just the standard algorithm like we did earlier. Notice there is no placeholder zero because you don't need a placeholder zero there. You really don't need it. You just have to remember that that 8 is in the tens place and that 4 is in the tens place. And then lastly, student 3, is this a valid method or did they get lucky? This student not only didn't get lucky, and not only is this method valid, but this is my favorite method of all time. And I wished that I had known this particular algorithm when I was a kid because I was never taught this algorithm until college. And once I learned it, it made everything so much easier. It's wild. We'll talk extensively about this particular algorithm, but this is called the expanded algorithm. Expanded algorithm. And we'll get to that in chapter 3, and I think it's actually lecture 3B. So I'll save it for that so I don't make this lecture too long. It's already pretty long. um, yeah, so analyzing incorrect or alternative solutions requires a specialized knowledge, a type of mathematical thinking and reasoning that goes well beyond just being able to do the calculation. You see what I'm saying? So teaching is very mathematical work. You've got to do all these things that are highly mathematical. You've got to analyze errors. You have to appraise unexpected claims, solutions, and methods. It's really, really fascinating. I love it because students come up with all of these wild ideas for how to solve things. And sometimes they're absolutely clever. They're just so clever. And I never would have thought of that on my own. Sometimes they don't. But we have to be able to figure that out as teachers. You have to be able to give and evaluate explanations, choosing and using representations. That's actually what we were talking about at the beginning with the slide on perspective, right? That same math problem, what was it, 14 minus 2, was easier depending on how it was represented. So that's an important distinction to make. How you represent something can make it easier or more difficult to understand. You're going to have to be able to choose and construct and use definitions. You'll have to make them yourself. You'll have to use them. Your students will have to use them. Interpreting and responding to students' ideas, generating simpler and more complex versions of a problem. For example, if a child is struggling with double-digit multiplication, back them up a little bit and do like a 2-digit times a single digit and try to see how they work the algorithm that way. And then see if you can make the problem a little more complex and see how it goes. Asking mathematical questions, you got to think of special cases, examples, counterexamples. A lot of times students will come up with a method and you'll be fascinated or amazed that it works. And then you'll start to say, well, does that always work? Does it always work that way? And you'll have to figure it out. You'll have to check. Maybe you can find a counterexample, or maybe that student's method was just a special case that only works in that case. And then recognizing and making mathematical connections within and across topics and courses, generalizing. So because mathematics is a language and it's just something we use to describe ideas, there are connections everywhere throughout your life, throughout existence, throughout your schooling, everything. Everything is connected in a very interesting and beautiful way in mathematics. Okay, so let's talk a little bit about standards, in particular the Common Core state standards. So in this course, we're not going to focus a ton on you needing to know exactly what those standards are and how to regurgitate them or which ones occur at which level. We're going to use these mainly as a reference point for us. That's what we're going to do. So we'll say, oh, this is what a student should know at this level in general. But for those of you that are going to go on to become math teachers, you really should start to check out these Common Core standards and start, um, I wouldn't say memorizing them, but just read over them and see what a first grader should know and what a second grader should know and what a fourth grader should know, and just familiarize yourself with them. Second here. Okay. This is also the website for the National Council of Teachers of Mathematics. They have a conference every year. You could actually go to it. You might even be able to get funding from the department. It just depends. This year, I think it's probably going to be all online, but it's good to keep track and see what's going on with those people. And then this is a link to the actual California state standards. So Common Core was implemented across the country during Obama's tenure as president, but not every state adopted it. And so that's why there's been this battle. We can talk about Common Core more in the collaboration meetings, and I encourage you to ask about it. My brief opinion about Common Core is that it's actually very amazing and it works extraordinarily well, but the program was not implemented correctly, in my opinion. I think it was implemented too broadly and too quickly. And so what I've noticed in my experience is that if somebody has a negative view of the Common Core standards, it's usually because they don't really understand what they are, or they had a teacher that absolutely hated them and had no problem talking to their students about how awful something was. You gotta take note of that. You know, as teachers, your opinion matters to your students, and so if you go out and start lambasting the Common Core standards, your students are going to carry that with them up into their future, right? So got to pick your battles, pick and choose what you say. Um, but yeah, California does follow the Common Core standards, so we are still on track in that way. Oh yeah, interpreting standards in textbooks is also mathematical work because you'll have to understand what they really mean. Here's a big overview. Common Core state standards, uh, the content standards. So up here you just have the different grade levels, and this is just kind of a survey of when loosely students learn and talk about certain things. First thing to notice is that geometry is constant. We teach students about geometry at every grade level, even from pre-K and on. We start teaching children about geometry from birth, essentially. Squares, circles, triangles, hexagons, things like that. In the beginning, we have to teach students about measurement and data. We'll actually talk about that in this course, but you know, when you're born, you don't know how to measure anything. You don't know what a foot is. You don't know how to measure anything. You don't know what a tape measure is. We have to teach that. That's a learned skill. Number and operations in base 10. Actually, over here, statistics and probability don't really start until middle school because you have to have a comfortable grasp of data and measurement before you can talk about those things. Number and operations in base 10, that's a huge part of elementary curriculum, just getting students to understand how to operate on numbers and with numbers, and to understand our numeration system, which is the base 10 decimal system. And that's actually what we're going to talk about in chapter 2. And then there's the number system in middle school. A numeration system is different from a number system. A number system is, well, we'll talk about that at the very end of the course, so I'll save it for then. But a numeration system is just a way of writing down numbers, and we'll talk about that in chapter 2. Operations and algebraic thinking, elementary curriculum, expressions and equations. This is when you start introducing more variables and doing actual algebra where you're talking about like completing the square and solving for x and those types of things. And this is actually a big point that I try to make in this course, and it's also a point of frustration for a lot of students in this course because a lot of times the problems that we are doing are rudimentary in the sense that they could be easily solved using algebraic techniques. For example, you could set up a system of equations and you could do like row elimination, or you could do substitution, and you can do all of these more advanced algebraic tricks. But the problems that your students have don't warrant that, and they don't know algebra yet. They don't know how to do that. So we'll talk about that pretty soon, actually. Counting and cardinality, that's an important skill that we start teaching really early on. There's some interesting research about pre-K cardinality abilities and counting abilities. Numbers and operations with fractions, that's grade 3 and up. That's when we start talking about fractions. You'll notice that it's actually quite difficult for students in grades K through 2 or pre-K through 2 to understand what fractions are. You can talk about a fourth and a third and a half, and they might have a basic understanding of it, but they're not really going to be able to keep it because they don't quite understand all these other things yet, right? Ratios and proportional relationships, we'll talk about that near the end of the course. I think that's chapter 9. And then functions, we won't talk about that in this course, but we save that for quite later on. Students don't really learn about functions in a rigorous way until the end of middle school. And by functions, I mean these things. There you go. That's an algebraic representation of a function, just to give you an example. That's an x, by the way. There we go. But yeah, we won't talk about those in this course, but you will in later courses. All right, so let's look at a couple specific standards. And what I want you to do is just pay attention to the verbs used in these standards. Okay, so this is one from kindergarten. So we expect a student to be able to do this when they exit kindergarten. They should be able to represent addition and subtraction with objects, fingers, mental images, drawing, sounds, claps, acting out situations, verbal explanations, all those types of things. So by the time a student leaves kindergarten, they should be able to do this. So if I say, like, what is 4 plus 5? Show me with your fingers. They should be able to say 1, 2, 3, 4, 5, 6, 7, 8, 9. Or they might even be able to say, here's 4 and here's 5. 4 plus 5 is 9. They should be able to do that by the end of kindergarten, definitely. Or claps or some sort of acting out, something like that, drawings, all that type of stuff. Here's one from grade 3. After grade 3, they should be able to identify arithmetic patterns, including patterns in the addition table or multiplication table, and explain them using properties of operations. So for example, you remember doing those multiplication tables when you were a kid? And like on the diagonal, you would have all the squares, right? You would have 1, 4, 9, I can't remember it in my head, 1, 4, 9, 16, 25, 36, right? So they should be able to recognize those patterns and explain why those patterns are there. There's other patterns too if you look at the rows and you look at the columns. So if you want, just pull up any old multiplication table, just Google it, and just look at the patterns. We expect exiting third graders to be able to identify those patterns and explain them using the properties of the operations. In other words, why does that pattern exist? Why is it that with the twos, it's 2, 4, 6, 8, 10, 12? That's interesting. Why is that? So a third grader should be able to do that by the time they leave. Here's a big one. This is after grade 5. So by the end of grade 5, students should be able to explain the patterns in the number of zeros of a product when multiplying a number by powers of 10. So let me just hold that for a minute here. So basically, when you multiply by a power of 10, like let's say you do 6 times 100, how do you know that that's just going to be 600? So a lot of students will say, oh, if I wanted to do 6 times 100, they'll easily know that it's 600. I'm sure you do too. Why? Why does it look like that? Why is it that we can just suddenly, like, it's almost like the 1 disappears and we just concatenate those things? Concatenate means to basically join like that. Why? Why? That's the big question, right? Explain it. So we expect exiting fifth graders to be able to explain why that works. And it gets more interesting when you start thinking about stuff like 23 times 100, right? That's 2300, but why? Why? That's the big question, which we'll talk about in chapter 2, I believe. Or how about this one? Look, explain patterns in the placement of a decimal point when a decimal is multiplied or divided by a power of 10, which we'll talk about in this course. So like, why is it that if you wanted to do 6.3 times 10, that's 63? Why is that? Who says? Who told you that? Why did you believe them? You shouldn't believe them. Don't believe anybody. Don't believe anything. You should be able to explain these things, and you should demand reasons and demand answers. The answers are there. If they haven't been told to you, it's just because they haven't been told to you. You got to ask. You got to demand. But we expect exiting fifth graders to be able to explain why that is actually true. Why is that actually true? Also, at the end of grade 5, they should be able to apply and extend previous understandings of division to divide unit fractions by whole numbers and whole numbers by unit fractions. This is something that we'll talk about a lot in the later module on fractions. So I'll save that conversation for that time. Yeah, same thing. So yeah, keep these in mind for when we talk about fractions. So one thing I can say is you'll begin your teaching careers at an exciting time, to say the least. For one, we're dealing with Common Core standards, and now we're dealing with quarantine and COVID-19, all that stuff. I'll have a brief discussion about it in a slide or two, I think. But it's an exciting time to be a teacher, an exciting time. And we need a bunch of brand new, really industrious younger teachers to step up to the plate right now, because you all are going to have a better connection with the students that you're going to be teaching than some of the older generation might. So that's the thing, as you get older, you will lose touch with the younger generations. You have to actively engage with them if you want to effectively teach them. So in some senses, it's almost better to be a younger teacher, because at least you know how you could sympathetically connect with the younger students, but you might not have the experience of an older teacher uh, with the knowledge of how to deal with certain situations. So it's really, really fun, I think. Um, okay, so this is actually from the Common Core state standards, and this is exactly what we're looking for. Because the big question is this: what does mathematical understanding look like? What does it really mean for a student to understand something in mathematics? Well, one hallmark of mathematical understanding is the ability to justify, in a way appropriate to the student's mathematical maturity, why a particular mathematical statement is true or where a mathematical rule comes from. So or I should say more concisely, we're just asking a student to be able to explain why something is true at a level of their mathematical maturity. So I wouldn't expect a highly rigorous explanation of the divisibility test for 5 from a child, right? But they might be able to explain it in a more rudimentary way that kind of shows you that they're going to be ready to learn the more rigorous explanation later on. That's really what it is. This is like a transition. It's like a moving up and a moving on for these students. In order for them to make this transition, they need really, really strong foundations, and that's what this is all about. K through 8 education is about getting really, really strong foundations, so that way we can have them do amazing things later on. And I'll talk about that a lot in this course. I'll talk a lot about how this concept that you first start talking about in like grade 2 is just to set somebody up so that they can do calculus later on without being totally confused. It's really amazing. Um, okay, so in addition to the Common Core state standards, there's also these standards for mathematical practice, or SMPs. So if you ever hear anybody refer to the SMPs, this is the list they're referring to. And the SMPs is a variety of expertise that mathematics educators at all levels should seek to develop in their students. This is a big one. Students should be able to make sense of problems and persevere in solving them. We'll talk about that a lot, actually. We're going to start talking about that in chapter 1, the next chapter. Um, they need to be able to reason abstractly and quantitatively. They need to be able to construct viable arguments and critique the reasoning of others. They need to be able to model with mathematics. Just being able to use some equations and push some symbols around, that doesn't really mean that you understand what you're doing. You should be able to model that in a meaningful way. And we're going to see that a lot in this course and your other MTED courses. Modeling is big. Modeling is big. Use appropriate tools strategically. So you got to know which tools are appropriate and when and how to use them. Your students, I mean, and you. We're all students. You're always a student. And attend to precision. This is the one that students hate the most, because there is a certain requirement of precision in mathematics, because if you lose that precision, then you lose the truth. And I would love to talk about that more in the collaboration meetings, but I don't want to droll on too long here. Look for and make use of structure. This is a big thing that we'll see in our first activity, actually. Look for and make use of structure. Activity 1A, I should say, not the first activity. Look for and express regularity in repeated reasoning. So be able to use repeated reasoning and express the regularity that occurs in that repeated reasoning. So those are the SMPs. Is that it? Yeah, that's all of them. Those are the SMPs. So those are good things to keep in mind. You actually might remember them as being like up in your classroom. If you remember elementary and middle school well, you probably saw those like on the wall, things like that, right? Let's see. Okay. Okay. So because we're in a particularly unique era, it's a good time to talk a little bit about COVID-19 and how it's going to affect education in the future. So one thing that you all future math educators should consider is just consider the structure and demands of remote teaching. for both you and your students, right? Uh, I'll say it as simply as this: teaching remotely is not just recording yourself teaching a live class. That's really the truth. It's not the same. You can't just basically go teach a live class and then record yourself doing it. That's not an effective way of teaching remotely. So if you're interested in teaching, you should consider these things now. Consider these things now. Consider virtual replacements and supplements, and we're going to do that in this course. Actually, we use a lot of manipulatives in math education, and because this is a remote class, a fully online class in quarantine, we're not going to be able to physically touch these manipulatives. So we have to find virtual replacements, and I have some. And consider the pros and cons of software. So for example, we're using a lot of different software right now: Zoom, Microsoft Teams, uh, Google, Jamboard, everything. We've got all these things. I'm actually using OBS to make my lectures because it gives me a lot more control over the video itself. And I have a lot of experience in video production from when I worked in Hollywood as a gaffer. So these are things that you should think about if you're interested in teaching, because online remote teaching is not really ever going to go away. It's going to be either integrated or it's going to become the norm, or what I think is going to happen is it's going to be offered dually. You're going to be able to pick and choose, because that's honestly what's happening right now. Um, and if you're, again, you should, for those of you that have younger siblings that are still in the K-12 education system, you should pay very, very close attention to what those institutions are doing to address this COVID-19 situation. Because speaking as a parent and as somebody who works at 3 different colleges and is also in a PhD program, I've been able to watch 4 different academic institutions at every level of education address this situation in 4 completely different ways. Uh, it's interesting. Anyway, develop comfortability with technology wherever you can and anywhere you can. Um, at this point, just if somebody's like, oh, maybe you should learn this particular piece of technology, just try to learn a little bit about it, or at least become aware of its existence. I'll say it like that: become aware of its existence. One of the things that has benefited me as a teacher and in my other careers is just anytime I'm introduced to a new bit of technology, I try to get at least a little bit comfortable with it. And the way that you do that is just this: you explore it by accessing every menu, every button, every click, every icon that you see. Anytime you get a brand new application, just look through every single menu item, and just look at it and see what it does. That's how you start. That's how you start. You don't have to be an expert, you don't have to master it, but if you just have a basic level of comfortability, it's going to help you jumpstart later on. Also consider video composition and presentation, because again, it's not just recording yourself teaching a live class, right? What you show on camera and what you don't show has an effect. The way it's presented, the size of things, those can all have an influence on how your message gets through. So for example, right now you're looking at the slides right over here. There you go. And then there's me right here in this little box. Well, that's because I specifically designed it that way, because I wanted the slides, I wanted the slides to be larger, and then I just wanted you all to be able to see me gesticulate in the corner. But you don't really need to be staring at my face the whole time I'm lecturing, you know what I mean? So there's no reason to be staring at my face the whole time. So those are things that you should consider going forward if you want to be a math educator in the future. It's actually pretty exciting, I think. Okay, so let's end this lecture with a look at this. This is a problem from the 3rd grade Smarter Balanced exam, the SBAC. Oops, sorry. Come back. There we go. The 3rd grade Smarter Balanced exam, otherwise called the SBAC. And just take a look at the question. The question says, Susan says that all of the figures are parallelograms because they have exactly 4 sides. Is she correct? Explain your answer. And then part B, this is after question 12. It says, what name, based on the number of sides, should Susan use to describe all of the figures, right? So firstly, the question is, are all of these parallelograms? And I'm sure if you all look at them and you think about them for a moment, you'll say, oh, no, they're not all parallelograms. But why? Why are they not all parallelograms? How do you know? Explain your answer. So first of all, answer it, and then explain why. And you'll notice that it's actually quite subtle. They almost are all parallelograms. They almost all are. In fact, there's only one figure in here that's not a parallelogram by most definitions, and it's this one. That's the only one that's not a parallelogram, which is funny, because some of you might be wondering, wait a minute, what about this guy? That's not a parallelogram. And I say, is it? Is it not? Why? Why do you think it is? Why do you think it's not? Explain. Explain. That's the whole thing, right? Yeah, if somebody's going to assert anything as being true, they need to back it up with evidence and provide proof that it's actually true. And if they don't, you should demand that. You should demand an answer. Demand an answer and ask why. Okay, so I think I'll go ahead and I'll stop there. That's the end of this first lecture, lecture 0, you could say. It was 1 hour long. Sorry, hopefully they won't be too much longer than this, but you'll see that they kind of vary in length. Other than that, I will see you all later, and I'll see you at the collaboration meetings. Have a good day.